Hello, welcome to this video. Today we're going to talk about Taylor series. This is the definition, you can say, of the Taylor series, and let me read it out for you. F of x is equal to the sum, then goes from 0 to infinity, of x minus a to the n over n factorial times the nth derivative of f evaluated at a. And how, what is this? How do we get to this formula? What's it even mean? Well, I'm going to prove it in the video, and then later I'm going to talk about what it's useful for, maths and in the world, in general. So, let's take this out and talk about how do we get to this formula. So, the goal of this formula is to write any function, and I mean any function, exponential, trigonometric, whatever you want, as a polynomial. So, something like C0, some constant C0, plus C1 times x. So we have the constant term, then we have the coefficients for the x term, then plus C2 times x squared, it's the x squared term, and so on. I'm just gonna present it when it adds an x squared, but theoretically, and how we do it is the polynomial extends till x to the infinity. Just goes on to infinity, doesn't add a specific x to the 5, 6, 7, 100. So, let's see. We want to find, what are those? C0, C1, and C2. So, the way we're going to do that is plugging in certain values of x into the function, and then seeing what comes up. Maybe stuff will cancel, and then we'll find values about all these constants. So, a thing you might notice is plugging into here, x is equal to 0. Why? Well, because here we have f of 0, just a number. We don't know which number, but just a number. Then it's equal to c0, the constant, plus c1 times 0, plus c2 times 0 squared. And then, anything times 0 will be 0. So these things will be 0. And I'll have left c0 is equal to 0. So if we write that down, at x is equal to 0, we have we have f of 0. So just this, plugging in at x is 0 is f0, obviously. It's going to be C0, this, then plus, like he said, C1 times 0, 0, plus C2 times 0 squared, 0. So plus a bunch of zeros, it's going to be plus 0, so it should just C0. C0 is equal to f of 0. Great. Now what do we do? Well, after thinking a bit, you might notice taking the derivative will give us that df over dx, the first derivative, is equal to the derivative of c0. It's just a constant, so it's 0. So I won't write that down. Derivative of c1 times x is c1, just the coefficients. The derivative of c2 times x squared is 2 times c2 times x. The 2 hops on, and then you subtract. Hops over, and then you subtract 1. So you get 2c2x. And then, similar thing happens. Plugging into here x equals 0, we'll get that we have the derivative df over dx evaluated at 0. Then 2c2 times 0, anything times 0, it's 0. Then plus c1, so just c1. Now we found what is c1. it's it's the first derivative evaluated at 0. And now you can probably see where I'm going with this. The second derivative will give us C2, and you're right about that. And we won't actually have to plug anything in. You'll see. So the second derivative, we just take the derivative of the first derivative to get it. And then it's going to be the second derivative. So d squared f over d squared x. And that is equal to derivative of c1, it's a constant, 0. Derivative of 2c2 times x is just the coefficients of x. So 2c2. And that's it. The second derivative is just a constant since the polynomial is from second grade. But we'll continue what we did, plugging in x equals 0 to fit in with all of this. We'll get that the second derivative evaluated at 0, so d squared f over d squared x evaluated at 0 is going to be 2c2. So what we'll do is very simple. Multiply by 1/2 on both sides. Multiplying by 1/2, and then multiplying by 1/2 will cancel. We'll have C2, but then this is not equal anymore because this will be equal to 1/2 of this. We multiplied by 1/2. So 1/2, the second derivative evaluated at 0. That's C2. And then we keep going with this. If we added an x cubed term, we'll be able to find out C3. It's coefficients of x cubed. C to the x to the fourth, C4. Just by repeatedly differentiating what we got. And, well, now let's generalize it. What we'll do is same thing. Let me actually erase all of this and continue with this. So and what I'll do is, like I said, continue with C3 times x cubed, C4 times x to the 4, and just so on to infinity. Like I said, the infinite polynomial we want to get. And then notice that that will not affect what we already had. And if thinking about it, plugging into here 0 would still cancel all of this. Powers of 0, 0. Multiply by anything is 0, so we'll just have C0 still equaling the function evaluated at 0. And then, taking the first derivative, we have all of those will hop over the exponents, so we'll have 2c2 times x, 3c3 times x squared, 4c4 times x cubed, and so on. But those won't matter since plugging in x equals 0 will cancel all of them out. And then so on. So what we will do is look generally. We look at the nth derivative of the function. And we'll see what it will give us. So let's imagine what it's going to be like. Well, taking the first derivative, c1 plus a bunch of x stuff, which will cancel and plug in 0. And then second derivative, 2c2. And then the third derivative, if you think about it, 6c3, and so on. But now, and then the rest is going to be some x stuff. So when you plug in 0, it's gonna all cancel out. The only thing we worry about is the constant term. So what is that constant term? Well, let's see. We'll ignore the constant and we'll see what's gonna be like taking n derivative of x to the n. One derivative, the exponent will hop, and then, it will hop, and then n times x to the n, and then minus 1. Next time it will hop again, times n minus 1, and then this will again minus 1, so minus 2, and then again another derivative, n minus 2 times n minus 1 times n times x, then minus 3. And then notice that at the kth derivative, we're subtracting 1 of the exponent k times, and we have k terms on the outside of n times n minus 1 times n minus 2 all the way up to n minus k. So if k will be equal to n, at the nth derivative, we'll have x to the n minus k is equal to n, so n minus n, times n minus 1 times n minus 2 all the way up to n minus n plus 1, since we need to have n terms here. N terms will multiply. Then x then minus n, x is 0, this is 1. So this is 1 multiplied by everything else. We can ignore that, so we can erase this. It's just 1, doesn't affect the answer. And then moreover, n minus n obviously will cancel here, and we'll end up multiplying until 1. So 1 times 2 times 3, all the way up to times n minus 1 times n. Does that look familiar? It's the definition of n factorial. And now that we've established what we'll have as the constant after differentiating n times, the constant is not this, it's going to be n factorial times the c of n. We still have all of those constants. So now erase this, so, and then the rest of all of those that were before constants, like say in the third derivative where we had 6c3, because then after the nth derivative, which is after the third derivative, say, then the derivative of those constants is going to be 0. So we don't have to worry about the derivative of the constants because they are all 0. You just have to worry about what's the constant, which is n factorial times c of n, and then plus a bunch of other stuff. I won't write that down. It's going to be x times a bunch of stuff plus x squared times a bunch of stuff, and so on. If you want to, you can look for yourself what other stuff, but it doesn't matter. Because we, like we did before, are plugging into here 0. So when we plug into here 0, you have the nth derivative of the function. So d to the nf over d to the nx, evaluated at 0. All of those cancel out because 0 times anything is 0. And we just have left n factorial times cn. And now, very simple. We divide both sides by n factorial, or multiply by 1 over n factorial. So times 1 over n factorial. This will cancel out, so I'll erase those. And then we're going to have to multiply by 1 over n factorial. And now we've established that the nth constant we have, c of n, is this formula. 1 over n factorial times the nth derivative of of f, the nth derivative of f, evaluated at 0. And now, this is super simple because now we can write this as the sum as n goes from 0 to infinity of Cn times x to the n. So at 0 it's going to be C0 times x to 0, which is C0, n equals 1. C1 times x, 2, C2 times x squared, and so on. But now we know what Cn is. Cn is this, 1 over n factorial times the nth derivative of f of x evaluated at 0. So we'll write this as the sum as it goes from 0 to infinity, and then we have x to the n over n factorial times the nth derivative evaluated at 0. But this is not the formula I wrote at the start. The formula I wrote at the start is more general with a. But now let me explain briefly why we can say what it was before. So we can imagine replacing all of those x's with x minus a. And then evaluating a into the function will end up being super nice. Because we'll have, instead of 0 to some power, I'll have a minus a to some power. But that's again just 0 to some power, which is 0. So everything will cancel out like it did. And the x will be replaced with x minus a, this x. And then the 0 will change to a. So I'm going to erase all of this. And then write the more general formula that I briefly explained why it's true in this. This 0 case is just a more specific case where a is equal to 0. Then, like I explained, this is the sum as it goes from 0 to infinity of x minus a to the n over n factorial times the nth derivative of f evaluated at a. And that's it. That's the Taylor series formula. But I don't want to end the video here because some of you might be thinking to yourselves, what the hell is this useful for? Sorry. What is this useful for? What is this? What is it useful for in math in the real world? Why? Well, again, the formula is for writing any function, and I mean any function, trigonometric, exponential, any function, just as a polynomial. Maybe infinite polynomial, but it's still a polynomial. And let me show you. So I promised, one of my last videos, I promised that we'll use Taylor series to prove Euler's formula. It's the I theta is equal to cosine theta plus I sine theta. Before I do that, I'll have to use this formula to write cosine of x, sine of x, and e to the x as those infinite polynomials. So e to the x is the nicest one. So let's start with it. So let's look at e to the x. E to the x is a very nice function because taking its derivative with respect to x will give you back e to the x. That is super simple, super nice. And because we're dealing with a lot of derivatives here, it's very nice. Because if we let that a is equal to 0, so we'll use this formula, we established is a more specific case of this formula, we are going to have as the nth derivative and e to the x, because any derivative of e to the x is e to the x, because we are repeatedly differentiating the past derivatives, which are e to the x. Meaning that for e to the x, we're going to have the sum, as n goes from 0 to infinity, of, use a specific case of a equaling 0, x to the n over n factorial, times the nth derivative, which is, like I said, e to the x, evaluated at 0, meaning that this x is replaced with 0. E to the 0, mean anything to the 0 except 0, is 1. Meaning that this is 1, multiplied by anything, it's still going to be the same thing, so we can erase this. And we have this formula. It's super nice. Sum, n goes from 0 to infinity, of x to the n over n factorial. And then, if we expand the formula, we get 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on forever. And we'll use this formula for e to the x, so keep this one in mind, because I'll erase this to have more room for sine x and cosine x. Because they are still nice, but not as nice as e to the x. So, well, let's see. Let's first look at sine x. We want to establish the nth derivative of sine x. What I'll do for that is write in a row the derivatives of sine x starting with the original function. So sine x, then its first derivative, then the second, the third, the fourth, so on. So what we'll do is this. Do what I said again. So the original function, sine x. Then the first derivative is very famous. It's the cosine of x. And then the second derivative is the derivative of the first derivative. So I'll take the derivative of cosine x. That is negative sine x. And negative cosine x. Then that's the derivative of negative sine x. And then finally differentiating this, we're back at sine x, and so we're back at sine x, and this will continue forever. We'll loop again because again we're taking the derivative of this to get the next one, derivative of this to get the next one. So plugging into the 0 is going to turn out like this. Sine of 0, 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. And then we're looping again. 0, 1, 0, negative 1, and so on. And that's what's really nice about this. It repeats itself. And that's what's the best for the Taylor series. And, well, let's plug it into the formula. So I'll erase this. And, well, let's see. Again, we'll use the more specific case where a is equal to 0. So, sine of x is equal to when n equals 0, it's just going to be the function evaluated at 0, which is 0, so I won't write that down. And next, we have the function evaluated, the derivatives. This first derivative of the function evaluated at 0 times x. So it's going to be, since it's 1, it's going to be just x. Then the next one is going to be 1 over 2 factorial times x squared times second derivative evaluated at 0. Second derivative evaluated at 0 is 0, so I won't write that down. Next up, we have minus, we have the third, when n equals 3, it's going to be x cubed over 3 factorial. And then all of the ones in the odd positions, when we plug in 0, it's just going to be 0. So we'll ignore when I have an even exponent coming up. And moreover, when we have an odd exponent, we're going to have the minus and the plus alternating, since those are alternating. 1 minus 1, 1 minus 1. So the next one, since it's alternating, it's going to be plus x to the 5th over 5 factorial. Then it's alternating, so we have plus, so now it's minus x to the 7th over 7 factorial, and so on. And it's easy to see the pattern here. It's not, I already said the pattern. And now I'll erase this, and a very similar thing happens with the function cosine x. It will eventually, the derivatives repeat. The row of derivatives is cosine of x, and then the derivative of cosine is negative sine x, and then derivative of negative sine is negative cosine x, and then the derivative of negative cosine is sine x, and then we're back to cosine x, and it just keeps repeating again. And then evaluating at 0, we get 1, 0, negative 1, 0, and then it repeats. 1, 0, negative 1, 0, and so on. And then plugging into the expansion of the specific case where a is equal to 0 in the Taylor series expansion, we get that cosine of x, plugging in those 1, 0, negative 1, 0, and repeat into the sum, the formula of Taylor series expansion, we get 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial times x to the 6th, and so on. And actually, I will leave it to you to replace x with ix and in the Taylor series expansion of e to the x, and then showing by powers of I that the real part is the Taylor series expansion of cosine x, and the imaginary part is the Taylor series expansion of sine x. So we'll get e to the ix is equal to cosine x plus I sine x. Again, I'll leave it to you because this video is getting way too long. Then, final thing I want to say is how calculators calculate the trigonometric values of sine, cosine, tangent, and so on. And how they do it, calculators use 5, 7, the absolute max 10 terms to get of these infinite sums to get a very, very high precision about the value of sine, cosine, but then the tangent, there are probably some infinite sums, but it's very simple. We can calculate sine, cosine to very high precision, and tangent is just sine over cosine, so that's very simple for them to do. Then the rest is also super simple. And that's just something I want to say. If you wondered how calculators do all these trigonometric, sine, cosine, tangent, all of that, that's how they do it. And finally, that's it. The video is getting way too long. Please subscribe if you want more content like this. And finally, that is it.